I'm a professor here in the physics and ECE department. And as I've noticed, a lot of the talks are very, very detailed. I love everything I'm seeing because I'm a details person myself. This is more on the kind of the less details. So it's how I've been trying to do science in terms of, initially you have to get grant funding in order to figure out how to build something, but my goal has always been to make it accessible by others, because as a kid I was so excited about doing science, but I couldn't afford any of this stuff that I kept seeing everywhere. And so I was trying to make it more affordable. So I developed a lab that allowed me to do that. So I'm located, let's see, we are here. No, we're there right now. My lab's, you can't see that, can you? No. It's opening up Steam or something right now, so just a minute. You can't see this. Okay. Well, you guys are in the middle of the map there. My lab is right over there, a few blocks away, and it's a nice lab, about 20 people, undergrads, volunteers, graduate students. I have people with PhDs that they get the PhDs from my lab, then they come back and they keep working because they love working in there. It's an environment where I like to have people be creative and develop new things. And a lot of the stuff we do tons of circuit stuff. But we use the circuits and the microcontrollers to build experiments and the things that people want in order to extend science further. These images, for instance, nice laser, if you're familiar with what a MOPA is, master oscillator power amplifier, or we do a lot of machining. I'm apparently in charge of the machine shop here in the College of Liberal Arts and Sciences right now, but hopefully we'll find somebody. Other types of circuitry, timing. I do a lot of femtosecond stuff, really fast. And I do a lot of, and that thing's out of focus. I can't reach that, too tall. So we do a lot of instruction as well, and we teach people how to do a lot of things. I teach E&M and a bunch of other classes, but one of them in particular, called the 316 class, is the physics course on how to put this stuff together and to build cool things, and to use it for science. And you do some science experiments too. So I want to talk about the experiments that a lot of my really clever people have done. Phil Witham, he's amazing. He came to me, had an idea, said, would this work? I said, probably, let's try it. And here's the idea. You have a vacuum chamber. You guys all know what vacuum is, right? In terms of, not your Dyson, okay. You basically pull down a good vacuum, you have nothing in there. Split the chamber in two, put some gas in one side, let's say helium. Other gases work too. Make a hole. What you'd expect to have happen is if you had a little hole, it would diffuse to the other side, right? You put an object there you want to image, the beaver. It scatters off and you collect it with a RGA you got off eBay. Very simple. As a result, you get this thing. It's made with plywood, PVC, tennis balls, other things, and some turbos and stuff. All off eBay. All this stuff on this thing was junk. I think there's a Raspberry Pi in there too somewhere. And basically, putting all this stuff together allows you to image with no lenses, no charges at all. You can just throw atoms at it, it bounces off, and you get an image. This is very useful because when you're looking at like low-K dielectrics, other things that get damaged by electron microscopes at higher energies, this won't. This is only tens of milli-eV in terms of energies coming off instead of hundreds of EV. So it's very, very useful. We've imaged a lot of things. You can image magnets because it's not ions, it's just atoms. You can image uncoated stuff. It's very, very nice. So this was a real success, and that student was just brilliant. He's amazing. I was hoping he'd be here today, but I don't see him in here, so. Another big effort, most people don't realize that we have a licensed nuclear reactor here, a fusion reactor actually. It's kind of hidden. But fusion, yes, I put the $ intentionally. A lot of money. One of my students is actually going there in a couple weeks and working on the sensors on this thing, but we do not have one of these. PSU doesn't have that kind of money. Actually, most single countries don't have that kind of money. But as you probably heard lately with the NIF and the work with the fusion Q factor and the fact that they got more laser, from a 2 megajoule laser to more than 3 output means that process seems to work. I won't say much about the 300 megajoules needed to run the laser, but the point is the fusion efficiency was awesome. And that's something that now gives us some hope, because it is a difficult process. People have been trying a long time, and there's a lot of configurations that people have done in order to make these things work. And obviously, only one place in the country, one place in the world can afford to do this with funding from a lot of different places. So other countries have done also things. I like the Stellarator, if you've heard about that. Talk about complexity, it's amazing. They knew that the donut shape of the eater system, the big tokamak, was gonna have like a twist in it, so they figure out ahead of time and make it so it compensates for the twist. It's kind of like a cruller donut, like what I have at the top there. Well, we can't afford this either. This is quite expensive. So we are on a smaller scale. We have fusers. Now this is one, an old one of the first ones made that got amazing results. It's something like 10 to the 10 neutrons, but it comes out to like 10 to the 7 neutrons per second. That's the indicator that it's working per kilowatt, which for the most part has been the highest record for a long time. We think we beat it recently, but an amazing design. The guy who invented this originally was the guy who invented the first electronic television, Philo Farnsworth. You know that name? Probably saw him on some sci-fis. He's like the other Tesla, you know. So interesting design. So we have a couple of these reactors, and they're doing quite well. We do a lot of modeling. We try to figure out, we build them, and then we do a lot of modeling of how this stuff works. And so we try to look at things like when particles are created and whatnot. See, this is the kind of fusion that you can do in your own house. That's what I want people to do. Safely. Neutrons are not safe for you, I will tell you right now. But being able to experiment with this stuff is very, very important, because a lot of money's been pumped into a couple different places. And the problem is, if we're gonna see more advancements, we need more people working on this kind of thing. So trying to develop this is really important. We found some interesting things about how this stuff is really working in this kind of configuration and design. So we've made some improvements. We do a lot of little circuit boards to develop the RF guns that we have, DC plasmas, all this sort of stuff, little detectors. So we have a lot of things to make that work. One of the things in order to monitor a plasma, a cool little board that Chris, who's brilliant at doing these little microcontrollers and whatnot, knows Verilog, all that sort of thing. So he pieced together a very nice circuit in order to look at plasmas, so we can determine the electron density, ion densities, temperatures, these kinds of things. Little thing, it just goes to your phone if you want it to and tells you all this, which is really nice, simple, doesn't cost zillions of dollars, and that's really amazing. This is on the ESP32, I can see, so you know, it's pretty nice. Another thing that we're working on right now is, I don't know if you knew it, but you can take X-rays. Well, you knew X-rays get images, but did you know if you can take low energy neutrons, it can get you an image too? And that's something that, you know, TSA, others are wanting to use more. And it has interesting contrast. You can see the grayscale definitely gives you more information than the X-rays do. But we need to use fast neutrons, because we got deuterons or deuterium cores hitting each other, generating fusion. They're going to generate neutrons and a couple other things. The neutrons have a very high energy, so you need to make them do stuff. And what the normal reactors do is it makes things heat up, and then you basically take a steam cycle and turn a blade, and you get energy. It's funny because, right, all this time, you'd think it'd be more advanced than that, but that's still what it is. It's a steam cycle, a little propeller turning, but that's fine. 60% efficient, that's fine. But the thing, there's other ways people are working on. But for this, we want to look at those fast neutrons, 2.45 MeV. That's really fast. It's like neutrinos, right? They don't want to be bothered by anything, right? Except for your body, because it has hydrogen, it interacts, it gives you cancer. So that's why you do have to be careful with this deuterium stuff. It doesn't have a runaway reactor. That's the thing, reaction. When you have a fusion reactor, it's not like when you smash the window on the chamber, it just shuts down. That's the good thing. It doesn't work the same way on a fission reactor. Fission reactor has a runaway reaction, but this does not. So it's a good thing to work on. We're looking at ways to look at, there's this cool thing by Texas Instruments, this little eval board that has really fast, I want to say 250 picosecond time resolution for for measuring like stop-start signals from neutrons. So that's one of the things we have. We have a really, really cool idea, but we're still submitting it in a grant. It's to be able to image stuff in 3D, the neutrons. So you can have a reactor and it'll tell you where all the fast neutrons are coming from and give you a beautiful three-dimensional image. So we're excited about that. Next time. Abdul's been working on a lot of things. He's building a 3D printer right now so that we can build the parts we need for the reactor. And that's a nice, cool little, you're familiar with the Nextion screen that goes on like a microcontroller. It's really cool, little touch screen. So it allows you we have a 1,000-watt laser for our 3D printer. And so you have to know what the power is. So I built this little power meter for it. It'd be nice if things were more easier to put together. So I see some stuff here that gives me a lot of promise that I can build this a little bit better than I did. We do a lot of the machining. Actually, we do all the machining ourselves, but with high tolerance, a lot of circuitry, nothing too complex. But in the end, it is complex to do 3D printed parts out of metal, especially when you're building it yourself. We have little things we want to do with this that are really cool. Another thing, I built this in my living room. My wife wasn't too happy about this. And it's a pulse laser deposition system. So it allows you to use, I watched Styropyro, and the guy had this awesome video on taking a tattoo removal laser system and being able to use it for certain applications. Well, I said, man, that's for me. Because I have billions of lasers, okay? But none of them have this kind of energy. This is incredible. It's like, at least it says it's greater than 1 joule. I haven't measured that, but it's so strong, it like ionizes the air whenever you turn it on. It's pretty impressive. But this thing has the ability, I can watch it as it hits a substrate and then does coatings. And if I put deuterium in there, the coatings can then be covered upon another and another and another. Then I can do target-based neutrons. And I'm getting like 10 to the 9 neutrons per kilowatt from this kind of trickery. So I can do a lot more, but that's for future stuff. What's this? Anybody want to guess? Solder ball? Here. I didn't think about the solder thing, but no, it's ball lightning. So I got together with David Griffiths, a couple of students from my class, said, let's write a paper on trying to make ball lightning and then measure its charge as it's floating around. So that's what happens when it's over. So everyone loves lightning, right? Unless it hits you, yeah. And so every once in a while, like what, every 10,000 hits or so, a ball comes out of it. And this isn't the kind of ball that we're talking about where it floats around and does weird maneuvers necessarily high up. The kind of lightning I'm thinking about, the ball lightning, is when it hits the ground, it liberates the ground because of the high current and high temperature. And when it does that, this little ball starts to form into a nice round ball of silicon primarily, because all the other things have been burned off. And so we figured out how to do it, and you take just chunks of silicon and you make it spark out. Someone else had figured out something like that. They thought you needed like super pure, but the fact that lightning hits the ground and you get ball lightning out of it, sometimes they're like 30 feet across, and they put all these nice colors out and whatnot. Either way, do not ever try to capture or let it come near you. I will tell you right now, because of what this is. This is burning silicon. It's molten, it flies around, and it flies around because there's a buoyancy, because what happens is silicon dioxide, perfect, I'll show you pictures of it, perfect little balls come off and cause it to float around. And they can last up to 15, 20 seconds, depending. You see this little guy there, but that's not the one. It's that one. He's still alive. He's still alive. So some of these last a long time. Unfortunately, David, I think, got hit by one of them. But you got to treat him. He wears Birkenstocks, so you got to be careful of stuff like that. So they bounce sometimes higher on the second bounce than the third bounce. It's interesting. And we realize because they're losing their mass. They're depositing it and melting whatever they're touching. They can go right through glass and make a nice hole. That's why I'm saying don't be friendly with it. And we tried doing it at first with something like this, which is a really big Marx generator that I put together, and found out this doesn't work. Even on the banana I tried to destroy, but it will destroy all the computers and all the electronics within so many feet. Found out you just go to Harbor Freight, get a little arc welder thing, and have just chunks of silicon off eBay, and I just 3D print a little box if you guys want the design. I have it. And you just, basically 2 plates, I put a high voltage supply on so I could measure the charge on the ball lightning.
Is it available for rent?
Oh, I just give you the files and you just make it. I mean, I think most of this has been destroyed now because I had to make room for so much stuff. But if you were curious, that's what the little balls come off. That's the smoke that you see is actually little balls of silicon dioxide. But I'd like people to play more with this and find new things from this. I have not tried to describe like the balls that do appear and disappear in space when there's no like lightning discharges. That's a different phenomenon. I'm not saying UFOs, I'm just saying they are different. And there is a legitimate kind that apparently does just appear. Maybe there's high voltages appearing, I don't know, from clouds, but they do appear and then disappear. Don't know what they are. Not a clue. Do you guys know anything about spectroscopy? Light, that sort of stuff? These are all different kinds of optical things that people are interested in order to identify what things are made out of. You basically have an atom, you shine light, it excites an electron, comes back down, emits some light. Depends on where you're going to and where you're coming from, the light can be different. So one of the things I tried doing, I got an NSF grant years ago to figure out, could I make imaging system so sensitive I could see a single molecule? And the answer is yes. And it did make it relatively cheap. And that was one thing that where I was from, they weren't interested in making it cheaper. You know, so I was. So the idea of that is you take light, let's say 400 nanometers, and you shine light on a molecule, and it might emit at 500, so longer wavelength. But another way is to do 2 photons of less energy, and you get the same photon out. You just have to make sure they're within 10 to the minus 17 seconds of each other. And so this one up here on the left side is the AFM scan, a topographic scan we made from scratch. And then the photon counts coming off of the surface, and we get really good resolution. You know about the diffraction limit? That you can't image better than lambda over 2 in general? Like you take 400 nanometer light, you excite something, you can't get better than 200 nanometers. This violates it, which is really nice. So we were able to show that you get all the way down to 5.6 nanometers with this technique. And I was trying to make it cheap as possible. Raman, same thing. These are single-walled nanotubes. And we went down the nanotube, and within just so many nanometers, we could tell it changed from one structure to another as you're going down the length of it. Oh, and those are the single molecules down there you can do. So we proved that you could do this, whether you used a $250,000 laser, a pulse 50 femtosecond laser, or just a diode laser. You can do the same thing. This is what you get with just normal diffraction limit. That's what you get with a trick. And the trick is you take a little nano antenna, you shine light on the little nano antenna that's resonant, and you can make a really, really strong field at the end of it. And here's that little, hopefully it's viewable. Maybe, maybe not. But a little point, so your spot's coming up from the laser, hitting this nano antenna, and you get this itsy little spot at the end of the probe, and that's what you scan with. And so I have papers on how to do that. The design for it, we made open source. Someone hacked our web page. We had to take it down. So if anybody's interested in this, write me an email, and I'll send you the whole design of how to make this microscope. That's the student's dissertation. So we made high voltage boards, H-bridges, preamps, phase detectors, you name it. There's a lot more boards. But when you put it all together, it's not bad cost-wise and whatnot. It's pretty good. We use parts from Thor Labs too to make it. And then we have we went further. One of my students, he works at Thor Labs now. He made a little autocorrelator. You've ever seen, I remember the first time I saw this, guy had a 10 or 15 femtosecond pulse from a laser, and he was showing it on a 1 megahertz oscilloscope. And I was like, this is impossible, right? How could you ever do this? This timing, it's impossible, right? But it isn't impossible. It's called an autocorrelator. And they use the same technology in order to get signals from space to determine if it's an alien or not at the Green Bank place. So it's a very cool thing. And you can see that pulse, that middle thing there, that width, full half max of that is about 50 femtoseconds in width. And you can see the individual attosecond level oscillations from it. But that's really cheap and easy if you want to make it. This is one I can't talk a lot about. I really do want to. This is like the ultimate. I want to train people on how to play with electron microscopes. You guys been over and seen Adam and Isabel's stuff over the electron microscopes? They're amazing trying to get 3 machines up and running like that. I would never attempt that. It's awesome. But basically, they work a lot with electron microscopes, but I would love it for more people to learn how to use these things. So we built something that's about the same cost as a medium scale, a couple $1,000, a 3D printer, but it's a SEM and a TEM. And it has a lot of technologies attached to it. And people will build it like you would build Prusa or something like that. So that's one of the things that I can't show you, but it actually works. The newer prototype is better because it has a design that students and anybody can buy it. If you have individual parts, it's all very modular and you can put stuff together. So it's really, really nice. But COVID kind of messed up the scheduling for all of this. So. And then the last, the course I teach, the 316, is where this is done by student Shane Meister. He did this thing where he's looking with an SDR system and then looking at our galaxy as it passes by, and you can see the signal. It's pretty cool. And then we teach people how to use electron microscopes, how to build high voltage systems, how to do circuitry in general on stuff. So they learn a lot of things, and that's a coolant-free cloud chamber over there. You just use some computer parts and some thermoelectrics. But easy access to stuff, doesn't cost a lot of money. That's it. I wanted to show you a lot more, but these are the people. Oh, don't forget, this guy, Surface Gizmos, if you do live in the area, he's got a lot of nice surplus. Has a lot of good things. But I'd like to thank everybody. Thank you.